Hi, this is laboratory experiment number 6. We'll be determining the molar mass of an unknown acid by titration. This is a classic experiment that nearly all general chemistry or AP chemistry classes partake in. In this case, we'll be doing it as a two-part method. I mean, you could just be given an unknown acid, you have some base, you know the concentration is, you'll add an indicator so that when the base is added to the acid, that moment that it passes past neutral and goes to acid, you'll get a color change so you know when it's been neutralized. And the more base you have to add to that acid, the stronger that acid must be in a proportional sense. And for this experiment, it is a 1-to-1 mole ratio. We'll add one level of precision to this. In other words, that base that we'll be dripping in, we're going to go ahead and standardize it. We're going to precisely determine its concentration. And in this case, how would you do that? Well, I guess you would drip in a acid. I mean, you would drip the base into an acid of known concentration. And you get to see that there's sort of a chicken and the egg issue where you could just keep going back and back and back. But we'll just be doing a standardization of our solution, and then we'll do our titration. The goal is to determine the molar mass of an unknown acid. Okay, so that's it. So there's two parts to it, the standardization part, that's here, and the titration part, that's here. So let's do them one at a time. First, we will be standardizing our sodium hydroxide solution. We know it's approximate molarity, but we want to figure it out precisely. Here's how we'll do that. We'll neutralize it with an acid known as KHP. That stands for potassium hydrogen phthalate. That would be phthalic acid if it was two CO2H's, but one of them is already been neutralized. So you still an acid right there. That H is the acidic proton there. And it'll just react with one equivalent of sodium hydroxide. That means one molecule reacts with one molecule, 1 mole reacts with 1 mole, and so simply KHP plus the sodium hydroxide will make a salt and water. If you're following closely, you could understand that it would be, in fact, the dipotassium salt of phthalic acid, since there's still one hydrogen left. All right, so it's just a 1-to-1 mole ratio neutralization. So we'll do this by weighing out some KHP in grams into a flask and then titrate it with the sodium hydroxide. Now, I'm not going to show you the explicit calculation, but I will show you the flow to determine the concentration of that base based on your data. So all you have is the grams of KHP that are in that, right? And you'll end up knowing how many milliliters of sodium hydroxide were required to neutralize it. So let's be clear. What do we got in here? Sodium hydroxide that we need to standardize. What do we have in here? A known amount of potassium hydrogen phthalate, KHP. From that, if you know the volume, and you will, you can figure out the molarity of that solution. So we have 3 of the 4 things that we need to know. We know the molarity of the KHP. We know the volume of the KHP. We know the volume that would be required to drip in here, and what we don't know is the molarity. So hopefully you can see that with that amount of data and the fact that it's a 1-to-1 mole ratio, we can calculate the molarity of the sodium hydroxide. Here's the flow. You know the grams of KHP. You should be able to figure out the moles of KHP based on its molar mass. From the moles of KHP, we should be able to figure out the moles of sodium hydroxide. Since it happens to react in a 1-to-1 mole ratio, those numbers should be the same. Once we have the moles of sodium hydroxide that were dripped in, we can figure out the molarity of the sodium hydroxide because we know the volume of sodium hydroxide that was dripped in, and molarity is moles per liter. Okay, that will give us a nice precise concentration of the sodium hydroxide that we need to use for the major titration that we want to do, which is to simply drip some of that base into an unknown acid and see how much has to be dripped in. The more base you have to drip in, the more concentrated that unknown acid must be in a proportional sense. So here's what we'll do. We'll determine the molar mass of the unknown acid sample, and in this case we'll do it similarly. We're going to weigh out the unknown in grams, and then we'll titrate it with the sodium hydroxide. That means we will have a solution here. Now in this case, the solution is the unknown acid. You do know the volume of it. You do not know the molarity of it. However, we will know the molarity of the sodium hydroxide. We just determined it. And we will know the volume we need to drip in. What happens is the moment it goes neutral, really, I mean, the moment the first molecule of acid persists, there's an indicator in here that once it turns basic, it will turn pink. Now, if you do this really nice, you should be able to get a pale pink endpoint, and I will demonstrate that for you. Okay, so here's this calculation, which once again, I don't want to show every step, but I will show you the basic flow. So here we go. Right there. You know the molarity of the sodium hydroxide, agreed? We calculated it there. From that, we can get the moles of sodium hydroxide, right? Moles per liter times liters equals moles. So you do that based on the liters that you had to drip in. You'll be converting from milliliters to liters. Once you have the moles of sodium hydroxide that were dripped in, you can calculate the moles of your unknown. There's a typo there. Because it's a 1-to-1 mole ratio. So once again, this number should be the same as that number, but I'd like to see a nice calculation with canceled units. Why do we bother doing that? Well, a lot of times it won't be a mole ratio. I mean, if this thing was the diacid, then it would be 2 equivalents reacting. But since it's not, it's just 1. Okay, so now you have the moles of your unknown, and from that you can figure out the molar mass, because molar mass is grams per mole. And where did you get the grams? Well, you weighed the stuff out to begin with. So I hope that flow is clear. Here's some reminders and some calculations. Reminders. Acids and bases are dangerous. They can blind you if they get in your eyes. I think I'm scaring you a little more than I really need to, but do wear the goggles. You do not want to get acid or base in your eye. Acids and bases can burn your skin, but if you get any on your skin, all you have to do is rinse it off. And they can put holes in your clothing, especially the base, so try not to drip any on you. We always say that you should, quote unquote, interpolate your volumetric readings, but that's just a code for saying anytime you're doing a measurement that has graduations, meaning little lines, be a good scientist and guess 1 unit. So estimate between the lines. There'll be a deduction if you don't do that. Condition your burette, and that means that if you're going to be dripping base into here, what if it had acid before from some previous user? Or even if it was neutral, that's silica, right? Silicon dioxide. It reacts slightly with base, and so if you just use clean glass, you'd get a slightly different molarity simply by pouring it in there. So what we'll do is we'll rinse it with some sodium hydroxide first, and then we'll add some fresh sodium hydroxide so it has been, quote unquote, conditioned. It always bothers teachers when they watch people run an entire 50 mils through here just to condition it. You don't need to do that. You'll pour a little bit in, swiggle it around, and you're good to go. And I'll demonstrate that as well, conditioning your burette. Once the liquid is in there, the sodium hydroxide, tap out the air bubbles. That should be obvious. You'll get a weird reading if there's a bunch of air bubbles in there. And here's the 400 mil beaker is available just for any waste. The 300 mil, 50 mil beaker is for the sodium hydroxide. And when you drip in your base into the acid, that moment it turns neutral, it should turn, it turns pink. And if you turned dark pink, it meant you went a little bit beyond. If you got it to the drop or better, it will be pale pink. And if you guys can show me your pale pink endpoints, that means you did it perfectly. Oh my God, you'll get super precise numbers. So that's always fun to shoot for that. Any waste will run down the sink, but you need to neutralize it first. The general rule is if it's pink, it goes down the sink. And here's the calculations we'll be looking for. These are 4 types of calculations only. I even added them up for you. I'd like to see 8 calculations, no more, no less. Let's see how they divide up. First, we need the molarity of the standardized sodium hydroxide solution. Notice that's the final answer here, right? The concentration of sodium hydroxide in moles per liter. I'd like to see you do that as one clean calculation. I do not want to see like 4 separate calculations that went into that, just one clean calculation. However, we're doing 3 trials, so I'd like to see 3 nice long linear calculations, each of which gives you the molarity of the sodium hydroxide solution for each trial, and then average it. I guess that's 4, right? 3 calculations plus 1 for the average, that's 4 there. The molar mass of the unknown, that's up here. The same thing. You can start with what you're given, which I believe in this case is grams of KHP, and punch it through using this sequence here to get the molar mass of the unknown acid. Once again, we'll be doing that for 3 trials, so they should be 3 linear calculations there plus the average. So 4 and 4 makes 8. So really the total is, 10 calculations, right? 4 and 4 makes 8, and then these 2 average deviations. For that average sodium hydroxide molarity, please calculate the average deviation. For the molar mass calculation, please, from that average, give me one calculation that gives the average deviation. That 8 should really be a 10. I hope you've followed through exactly what we're looking for. Hey, in lab, if there's any issues, just ask me. You could search that lab over and over again, and it will not tell you how to do the average deviation, so I took the liberty of showing a sample calculation. There's the average for a bunch of data. And to get the average deviation, just have each do it this way. Find the difference for each one, divide it by the number of numbers you have, and it'll give you the average deviation. So this would be a value of 9 plus or minus 2.25. Okay, that's what we're looking for today. I look forward to seeing you guys Wednesday. Email me if you have any questions. See you next week.